Making accurate power integrity measurements continues to increase in importance. As rail voltages get lower and tolerances get tighter, getting accurate ripple and noise values gets harder, as the measurement system of your scope and your probing system can interfere with what you're trying to measure. Here are 5 tips that will help you get more accurate measurements. First, it's always best to start with a scope that has low noise. Your scope will never take a more precise measurement than the amount of noise that it has on it. How do you determine how much noise your scope has? It's very easy. Here I've disconnected all of the inputs from the front of the scope and I've turned on a noise measurement. At 10 millivolts per division and 2 gigahertz bandwidth that this RTE has, I can quickly determine how much noise I have. In this case, a little less than half of a millivolt, which is impressive for scopes of this bandwidth and vertical setting. Second, achieve sufficient offset. Scopes typically don't always have enough built-in offset to allow users to place the waveform at the center of the screen and expand. Blocking caps or using the AC coupling mode on the scope will remove the low-frequency DC components. This solves part of the problem, but it eliminates the ability to see true DC values and drift. Look to solve the problem using a probe that has built-in offset. In this case, the ZPR20 has plus or minus 60 volts of offset to center the signal. Third, use the right probe for the job. How much difference does a probe make? It's huge. Let's look at a comparison between 2 probes. We're going to take some measurements using a 10-to-1 passive probe, and then we're going to take some measurements using the ZPR20 that has been specifically designed for power rail measurements. For my first measurement, I'm going to use a 10-to-1 passive probe. Probes that have higher attenuation ratios amplify noise, and poor grounding can also impact measurements. In this case, we've taken a measurement that's almost about 100 millivolts peak to peak. And if you look at the signal on the screen, you can see significant noise in the waveform. Let's go ahead and switch to a nicer probe using the ZPR20 power rail probe. With the ZPR20 power rail probe connected, we see a much cleaner signal with very, very little noise. If I press single, it looks very, very sharp and clean. And you can see that the amplitude measurement has been reduced to about 46 millivolts. Fourth, to further improve the measurement, use the most sensitive vertical scaling possible. This has 2 distinct advantages. Your scope gets to use more of its ADC dynamic range to make for a more accurate measurement, and you'll have noise reduction as total noise is a function of full screen value. The smaller the amplitude of your full screen value, the less noise your measurement will have. Let's take a look at it on the scope. Scaled at 40 millivolts per division, I have an amplitude value of just under 51 millivolts peak to peak. If I change the vertical scaling to a more sensitive setting, say 5 millivolts per division, I now have a more accurate amplitude measurement of 44 millivolts peak to peak. Fifth, reduce broadband noise. Your oscilloscope will have a certain noise level per hertz. The more bandwidth your scope lets in, the more noise each measurement will have. Let's take a look at it on the oscilloscope. Here at 2 gigahertz bandwidth, I have an amplitude measurement that's about 45 millivolts. If I bandwidth limit, for example, to 500 megahertz, press reset on my statistics, I'm now making a peak-to-peak measurement that's about 39 millivolts. Before reducing bandwidth, make sure you know how much bandwidth your measurement requires, including capturing the signal, its harmonics, and any sources that might be coupled on the power rail. In summary, if you remember, we started with a volt peak-to-peak measurement of just under 100 millivolts. We got to a point where we more accurately measured just 38 millivolts. Remember, most importantly, using a low noise scope and the right probe for the job makes the biggest impact on measurement accuracy. Thank you for your time.